Hi all, my name is Stephanie Sierra, and I'm a senior majoring in mathematics and computer engineering. This year, I had an awesome opportunity to do research in the mathematics department at Meredith College with Dr. Hans. While searching for a mathematical topic to do my research on, I realized that I'm a visual learner, and I wanted to select a topic that was more visual rather than the usual equations and numerical analysis. With that being said, the topic I chose primarily focused in graph theory, but more specifically graph coloring. So I looked at the diagonal chromatic number of maximal planar graphs. When we think about the word graph, we all think about different valid forms of graphs. For example, a person interested in business could consider a graph to be an x, y axis with a trending line. Or for others, it might be a GPS they use to navigate from one location to a destination. Graphs are all around and their possibilities are endless. However, in graph theory, graphs are mathematical structures that consist of both vertices and edges, where vertices are the nodes and the edges are the lines that connect the nodes. There are infinite ways to construct graphs, but the graphs that we will consider in this presentation are constructed based on the diameter between vertices. But before we dive into looking at the diameter of a graph, we must first understand the definition of distance. The distance between two vertices is the length of a shortest path connecting the two vertices. If there are multiple paths that connect the two vertices, then the shortest path is considered the distance. For example, in the figure below here, we're going to try to find the distance between vertex A to vertex B. So first we must consider all paths. So we can take a path from A to C to D to B to get from A to B, or we can do A to D to B, or we can do A to B. And obviously the shortest path is A to B, so the distance between vertex A and vertex B is 1. The diameter, on the other hand, is the greatest distance between any two vertices. So if we look back at this figure right here, the greatest distance, so we would have to look at every possible combination of vertices. So if we look at A to B, it's 1. If we look at A to D, it's 1. If we look at B to D, it's 1. But if we look at C to B, it's 2 because it's there's only 2 ways we can get from C to B, so it's CAB or CDB, which means that the diameter is 2 because that's the greatest, shortest path connecting the two vertices. Planarity. So a graph that can be drawn on a plane so that no two of its edges cross each other is called planar. Um, So in the figure below on the left, that figure is non-planar because as you can see, there's multiple edges that intersect with other edges. My research focused on the structure of maximal planar graphs. A maximal planar graph is a graph where every face is a triangle or bounded by 3 edges. Um, and a maximal planar graph also has to follow planarity, to which no new edge can be added without crossing each other. So on the bottom right graph, you can see that one is maximal planar because every face on the triangle, in the graph is a triangle, and there aren't any edges that cross each other. So that's what makes it maximal planar. Um, if you look closely at it, these graphs are isomorphic because each of the vertices do still share an edge with the vertices over here in the non-planar graph. And so they're isomorphic, except that one graph is maximal planar and another is non-planar. So an ongoing topic that is still very active in the field of research is graph coloring. Graph coloring is the assignment of colors to vertices or edges in a graph. A subtopic underneath graph coloring is chromatic number, which was first introduced in 1852 by a mathematics professor in London. And the chromatic number is the smallest number of colors needed to color the vertices of a graph such that no two adjacent vertices have the same color. So in this very simple graph here on the right, if we look at vertex A and we look at all the adjacent vertices, they shouldn't have the same color as A. So B is red, D is purple, C is yellow. So that's a valid graph. And if we go individually and look at every other node or vertex, the same rule applies. And in this case, this is the chromatic number of this graph is 4. However, you can reduce this number if we colored vertex C with the color red, because C isn't adjacent to B. So that means that the chromatic number of this graph is actually 3. So there are many subtopics related to graph coloring and chromatic number of a graph. In 1987, there is a similar concept to chromatic number that was introduced. It's known as the diagonal coloring of plane triangulations, also known as the diagonal chromatic number. The diagonal chromatic number is the smallest number of colors needed to color the vertices of a graph such that two adjacent or diagonal adjacent vertices are of different colors. So not only are we looking at the vertices that are adjacent to a vertex, but we're also looking at the vertices diagonally across from the vertex, and we have to make sure that they're not the same color. So for example, let's take a look at the figure on the right. If we begin at vertex B and we look at the vertices adjacent to B, which are D, F, A, and C, we can agree that the vertices adjacent to B do not have the same color as B. So D is orange, F is pink, A is green, and C is yellow. Now, if we look at the vertices diagonal to B, which is just E, and how did I figure that out? Well, because when I look at B, I look at the edges where I can like create a fold, and I can see like what edge kind of what vertex match B. We can see that vertex E is diagonally adjacent to B and shouldn't have the same color, which in this case it respectively follows. So in that case we would assign E a different color. And if we look at the same thing for D, if we look at the adjacent vertices, they're all different colors. And if we look at A, which is diagonally adjacent to D, it's also a different color. So, and if we continue this pattern just to make sure that all the vertices adjacent to each vertex isn't the same color, we find out that the diagonal chromatic number of this graph is 6. So you may wonder, like, how is the diagonal chromatic number different from the chromatic number of a graph? Well, let's take the same graph from the previous slide and find the chromatic number. As you can see, we're not really worried about the diagonal vertices. So that means that they can be the same color as the um, at, as the vertices diagonally adjacent to that vertex. So for example, we in the other graph, we said B and E had to be different colors because they were diagonally adjacent. Well, in this case, since E isn't directly adjacent to B, E can be purple as well. Or if in the case of D and A, in the other graph, they had to be different colors. But in this graph, they can be the same color. So if we, by coloring this whole graph, um, this makes the chromatic number of the graph 3, which is half of um, the diagonal chromatic number from the same graph. In my research, there are 3 main classifications of graph that we will evaluate. Each of these graphs will have a diameter of at most 3 and a maximum of 12 vertices. But the 3 main classification of graphs that I evaluated was a triangle, square, and a pentagon. And they all had the same form of expansion. They each all have 12 vertices, no more, no less. And then they were all maximal planar and their diameter was of at most 3. So they were each constructed in a similar way, just that their base or initial structure was a different shape. So you're probably wondering why I didn't look at a hexagon or an octagon. Well, because if you look at the, in order for it to be a maximal planar graph of 3, those graphs required a minimum number of 15 or 20 vertices to be constructed or be considered as a maximal planar graph of diameter 3. So I didn't really look at those. I just wanted to find 3 graphs that were similar and could be expanded in the same way and see if they had a relationship with the if each of these graphs had a common diagonal chromatic number. So I decided to just stick with these 3. So the triangular structure has many unique characteristics. If we look at the initial figure of this particular structure, which is just a triangle, I noticed that the figure is maximal planar, which means that no additional edges need to be added, which isn't the same with the other figures. Also, the structure requires a maximum of 3 vertices to isolate the initial structure from the rest of the graph. And when I say the initial structure, I mean a triangle. So if I were to remove vertex D, vertex E, and F, that would result in isolating the triangle ABC from the rest of the graph, which isn't the same for the other graphs as well. And this graph was pretty interesting because it only needed 8 vertices to classify as an MP3 graph, unlike the other graphs where it needed 12 or more vertices to classify as the MP3 graph. The next structure that we'll look at is the square structure. I know these are kind of plain names, but they made sense to me. And so with this structure, if you look at a regular square, 3 additional edges needed to be added for that figure to be considered as maximal planar. And so And like I said before, this graph also needs a minimum of 12 vertices to be a maximal planar of diameter 3. And then in order to isolate or remove a triangle from this figure, you need to at least 5 different vertices need to be removed. And then if you want to isolate the initial shape, which is a square, a four-sided figure, or a figure that had 4 edges, that required at least 4 vertices to be removed. So if we wanted to isolate the A, B, C, and D, we'd have to remove E, H, G, and F, which were vertices diagonal adjacent to those 4 vertices. The next structure that I looked at was the Pentagon. So the Pentagon, of course, is a 5-sided figure. It needs 4 additional edges to consider the base as maximal planar. As you can see in the initial shape or in the initial structure, you can see the Pentagon is constructed with the vertices A, B, C, D, and E. And then in order to make it maximal planar, we needed to add those, or at least, yeah, maximal planar. We needed to add 2 edges in the middle to make every face of this figure to be considered as triangles or bounded by 3 edges. And then in addition to that, 12 vertices were needed to make the graph maximal planar of diameter 3. And then this graph is considered to be different from the other graph because it needs at least 4 vertices to isolate a triangle in this figure, and then 5 vertices needed to be removed in order to isolate the initial structure, which is the Pentagon. So for the graphs that I created and expanded, I determined that the diagonal chromatic number of these graphs was 6. One graph that I found to be pretty interesting was the triangular structure, because you can alternate 2 colors on one side of the triangle as long as you continue to expand the graph in the same pattern or way. And so if you can see, like, if we go down edge we go down the side of C, and we're looking at the vertices C, E, H, and K, they all alternate the colors blue and green, and that pattern will continue as long as you expand the graph in the same way. So if we continue to expand this graph, the pattern stays the same, so that means that the diagonal chromatic number of this graph will always be 6. For the other graphs, if we were to expand them, then the diameter of the graph would change, and then the diagonal chromatic number would change as well. But in the way that I expanded and constructed the graph, the results ended being that the diagonal chromatic number of the structures is 6. Thank you for watching and listening. I am so thankful for being given the opportunity to do this. I learned so much, and I couldn't have done it without Dr. Hunt, so thank you very much, Dr. Hunt. I really appreciate the time you took to guide me in the right direction, and I couldn't have done it without you, so thank you.